Okay, in this problem we are asked to find CV and Cp of carbon dioxide at a given temperature and pressure. And they said use 1K as the difference in setting up the neighboring states. Okay, first let's recall what is the meaning of the property CV, specified at constant volume. It's defined as del U del T at constant volume. Well, it looks like a complex partial derivative, but if you think about what it simply means how U changes, U the specific internal energy changes with temperature if volume is kept constant. So in other words, if we can do an experiment how U change between state T1 and T2, state 1 and 2, if we hold volume to be constant. So if we think of two different states, neighboring states, and change temperature and see how much U changes, their ratio should be CV. And it's given that use 1K as the difference. In other words, T2 minus T1 should be 1K. So we can set up two states, state 1 with, of course, the pressure is given to us. Pressure equals 100 kPa. So temperature at 1 should be about 1000 kPa, but we can say 1000 minus 0.5. So that will be one of our state. What should be our state 2? Well, we don't know what happens to pressure. We know volume remains constant. So V2 must be equals V1. And T2 is 1000 plus 0.5, 1000.5 K. Oops, this should be K here. So we are going to set up two states, one with pressure 100 kPa, temperature 995, another with volume remaining the same and 1000.5, and we'll figure out what is U2 and U1 and their difference, and from there we can figure out what is CV. So let's start the IG state test calc. How do we do that? I've already logged in thermalfluids.net. Let's go to test calc and let's launch, because we are interested in properties, let's launch the system test calc. And what is the IG model? Well, you notice all the gas models are here. So we click on the IG model. Now there are different tabs here to get it started. We click on IG test calc, and in case this doesn't show up, look at the Lego button over there. You have to allow Java. If Java is allowed, then you just say run. Okay, so let's get started. We first select the gas, which is CO2. And what is given about state 1? 100 kPa and a temperature of 999.5. And this is called central differencing. I could just choose T1 as 1000 K and T2 as 1001 Kelvin. That's called forward differencing. Anyways, so we know the pressure and temperature. We click on the calculate button and you see that U1 is calculated. I mean, look at U1, so negative. That's because something called formation enthalpy has been added, but it doesn't matter. It's all relative how energy is measured. It's always based on what do you call zero energy. So don't let the negative sign bother you. For state 2, what is known? The temperature is 1000.5 and the specific volume remain constant. So we can say V2 equals V1. And the state is calculated. Notice that another U is found. That doesn't matter. We can just go here and on the IO panel and find out the partial. How? It's simply U2 minus U1 divided by T2 minus T1. So what we calculate is 1.045. So if you go, so we found CV to be 1.025. I believe it was 1.045. Well, but if you go to the state panel, notice that CV, CV is not produced, but CP value is given here. And we know that CP minus CV equals R, so one can show that the CV value we got is pretty close to the actual answer. Okay, let's go find out what is CP. Once again, we know from the definition of CP, CP is given as del H del T at constant pressure, which is equals H2 minus H1. We use state 2 and 3 already. So let's say it's H3 minus H1 divided by T3 minus T1 when you hold the pressure at state 3 same as pressure at 1. So we already have evaluated state 1. We are going to find a neighboring state 3 where we'll hold the pressure to be same as state 1 and we'll make the temperature to be 1000.5 Kelvin. And that will produce our CP, which will be equals H3 minus H1, T3 minus T1. So let's go back to the test calc, and this time we'll evaluate a state where we'll hold pressure 3 to be constant, equals P1. And the temperature equals 1000.5. Of course, that will produce all kinds of properties, as we can see, using the thermodynamic relations. But our goal is to just evaluate CP. We know CP is defined as how enthalpy changes from state 1 to 3, H3 minus H1. I'm doing, of course, T3 minus T1 will be just 1 Kelvin. So this is 1.234. So what you get for CP is 1. So that's our approximate answer that we, like an engineer, we evaluate the derivative. It's not like a mathematician. If you go and take a look, the exact value of CP is, look at that. CP is produced as part of the state, and what we found from the fundamental principle is not different from what TEST has calculated, 1.234, and what we found manually is also 1.234. So you can see the definition of CP, where you have to take a partial. Instead of taking a partial, we basically use differences, small differences, to find the ratio in the spirit of what is limiting value. Of course, to get more accurate value, the difference in temperature should be even smaller. But in a computer, you cannot make temperature difference arbitrarily small because your data may not be so accurate. Anyway, so we found the value of CP and CV using fundamental definitions.